Okay, so we'll maybe wait 1 more minute and then we'll start. Okay, so we'll start now. So this is the third class in this lecture series, and the last class we covered quite a few things. So I've kept this all the slides here for the important information, the meeting link and stuff. The references we are following is Ozar. I hope everybody has attended either of the two classes or gone through the lecture. I'll maybe skip over this. So yeah, we are doing chapter two, the module two from uh, chapter one actually in Ozar. It's electromagnetic theory. So in the last class, we covered Maxwell's equations and wave equations. Started with wave equations. Let's do a quick recap. So these are the Maxwell's equation, their notations. So these slides we have already seen. We'll just do a quick recap and then start with today's part. Uh, the differential form, the integral form, the constitutive relations that completes the Maxwell's equations. We looked at the time harmonic fields. For example, if a particular wave has a varying with a particular vector quantity is varying with omega frequency, we can represent it in terms of a phasor, and by using this derivative, and we can replace the d by dt into j omega in the Maxwell's equation. We also looked at the polarization and then the boundary conditions. So we gave a relationship between the electric flux, the electric field, and the polarization, which we defined the polarization for a linear media like this. And then we looked at the complex permittivity. Similarly, we took the Ohm's law, modified it, and then modified the Maxwell's equation for magnetic field to get the relationship in terms of the relative permittivity. So yeah, so we replace this term as epsilon, and that is relative permittivity, and then we define the term known as the loss tangent. We also looked at discussed something about the anisotropic and isotropic media. So and for an we also discussed for that for an isotropic media, these non-diagonal terms will become zero, and this diagonal term will become equal to one particular value. But that is, we are multiplying a constant to an identity matrix, and that will simplify the media to an isotropic material. For anisotropic medium, the all these in terms in the tensor is different. Then we did the similar study for magnetic field. So we gave a relationship between magnetic flux, magnetic field, and the magnetic polarization, and we defined the magnetic polarization in terms of magnetic susceptibility. Again, we defined the complex permeability of the medium. And similarly, for an anisotropic medium, defined in terms of magnetic permeability, as given in this form, where this particular tensor defines the uh, way in which the magnetic flux and magnetic fields are related. And similarly, if this reduces to a diagonal matrix with these values same, and it will become an isotropic media. And so hence, these are the Maxwell's equation that we have defined. And over here, the mu and epsilon are the complex permittivity and permeability. Then we discuss the boundary conditions. So there may be when a wave propagates from one medium to the other, for example, from medium one and to medium two, where the properties of medium one are defined by epsilon one and mu one, and for properties of medium two are defined by epsilon two and mu two. We have to apply the boundary conditions to get the fields. If we have the field in one medium, then to calculate the fields in the second medium, we have to consider the equations of the boundary. These come in handy if you are doing computational electromagnetics. You'll have to take care of the fields when they uh, move from one medium to the other. So we basically decompose the magnetic field and electric field into the normal and tangential components and work on them separately. So for the normal components, we usually take this what we call this pillbox kind of structure volume. So this particular cylinder or pillbox is kept at the boundary, and we then what we do is we make this H tend to zero. So we end up with two surfaces and with negligible volume, and then we use the Maxwell's equation and simplify it so that we get the relationship between D1 and D2, which is the electric flux in medium 1 and medium 2, and which is dependent upon the charge density contained within this particular surface. Similarly, when we do a similar formulation, we will get the relationship between the magnetic flux in both the medium. Now, if, for the tangential components, what we do is we take a surface integral, take a surface over here, and use the Maxwell's equation where we on the left hand side we have the line integral of the electric field and surface integral of the magnetic uh, flux and the magnetic uh, current density. And then what we do is again we make this h tend to zero, the height, one of these sides of the surface, and what we end up with is two line integrals and two lines and one very and a surface with a diminishing surface area. So and then we simplify it, and then we end up with this relationship where the tangential electric fields are, if you write in terms of vector, the electric field in region 2 and region 1, when we take the cross product to the normal vector, is equal to the magnetic current density of the present on the surface. And a similar uh, thing can be done for the magnetic fields as well. uh, Using the previous derivations, we can uh, make three different cases in which if the medium one and medium two both are dielectrics, either medium one or medium two may be a perfect electric conductor, and either of them could be perfect magnetic conductor. So under different like if these mediums change, we will end up with a different set of boundary conditions. Now, then we started with the wave equations. So, and we saw that the wave equations are given by uh, the Helmholtz equations. And for a linear isotropic and homogeneous medium, the Helmholtz equation will look something like this. And we define the velocity of the wave propagation and the propagation constant or the wave number of the uh, propagating wave. I've left this as an exercise for you to derive wave equations from Maxwell's equation. No worries. I think I'll share the results maybe after class or by tomorrow. We won't discuss this because this is very standard. Maybe we can refer to the textbook. And then we looked at the propagation of a wave, plane wave in a lossless medium. So we started with the Helmholtz equation, and since the and we took a very simple case where the electric field only has an x component, and 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 there is no variation of the electric field in x and y directions. So the Helmholtz equation will reduce to some this particular differential equation, and this differential equation solution can be given by this, where e plus and e minus are just arbitrary amplitudes, and we can similarly write this in time domain in this form. Okay, so once we have so we can give the solution in either frequency, this phasor or this time domain form. And then we defined the one of the properties called the phase velocity, and we derived its relationship with omega and k and mu and epsilon. Did a quick numerical on calculating the phase velocity of a wave traveling in free space. Then we defined the wavelength and derived the relationship between the wavelength, the phase velocity, and the frequency of the plane wave. And then since we had discussed everything in using electric fields, and to find out the magnetic fields, we once we have the electric field, we can just using the Maxwell's equation itself, we can just put the value of electric field and calculate the magnetic field's value. And then we defined what we know as the intrinsic impedance of the medium, which is a property, which is the property inherent to to that particular medium, and it is related to mu and epsilon in this fashion, root under mu by epsilon. And we did a quick numerical then to calculate the intrinsic impedance of free space, which uh, which turned out to be 377 or 120 pi ohms, and remember this number. This comes in handy quite often while doing numericals. We did this particular numerical where we had uh, a wave propagating uh, in dielectric medium. Yeah, and we know the frequency of the wave as 5 gigahertz, and we have the expression for electric field, and also we had the wavelength of the wave in that particular material. We were supposed to find out the propagation constant, the phase velocity, the relative permittivity, and the wave impedance. So up till now, whatever we had discussed, we used that knowledge to calculate the propagation constant, which was 2 pi by lambda. And then the phase velocity could be calculated by using lambda f or omega by k. So whatever information is needed to calculate the O terms were already given. Yeah, so we did this numerical. Okay, so today we will start with plane waves in general lossy medium. Uh, we know that the loss in a medium is given by the imaginary part of the permittivity or permeability. And yeah, so if a medium is conductive, we give it, and we have defined its conductivity as sigma. The Maxwell's curl equation can now be given by uh, the Maxwell's curl equations are given by this. So we have this term coming up over here. So this is the new term. So we have to make sure we take into account while doing all the calculations. Now the resulting wave equation for the E field then will look something like this. So earlier this particular term was not there, so it was just del square E plus omega square mu epsilon E equals 0. But now we have this particular term over here, and then for this also we have earlier defined a propagation constant, but this time since we have an imaginary term over here, the our propagation constant will look something like this. So we define it as alpha plus j beta, and take the root of this particular part over here. So we'll have this j omega root under mu epsilon, again root under 1 minus j uh, uh, sigma by omega epsilon. Now, this alpha and beta are actually the attenuation constant and the phase constant. So the alpha actually results in the decaying of the wave when it propagates through a medium. So if we want a wave to propagate in a medium without any attenuation, this alpha should be 0. Again, so if we assume the electric field is only in the x component, like we did in the previous case, the Helmholtz equation will become something very simple like this. So just instead of k over here, we are writing gamma. So the only change we write now is over here, and this gamma actually incorporates the sigma by omega epsilon term. Again, the solution will be given the same similar expression. So we already saw this in the previous class. And now we know that the positive part is actually given by so the wave propagating in the positive direction is given by this particular given by the term which has e power minus gamma z, and we can then again substitute the gamma by alpha plus j beta, and we end up with two this e power terms, and this e power and again this writing this in time domain will result in something like this. So this j beta z can be easily changed to cos omega t minus beta z when using high school mathematics. We know this transformation between Euler and these phase terms. And then if you just remove the loss, we'll end up with gamma equal to jk, and alpha will become 0 and beta will become k. So this will then revert back our formulation to the lossless medium. Now, we can also do the same treatment, but instead of using sigma, we can use epsilon as epsilon dash minus j epsilon double dash, and that we end up instead of doing all these things, we just write epsilon in terms of epsilon dash and epsilon double dash, and then we have this formulation using tan delta. So both of these things are equivalent. You can either use this treatment or use this treatment. For example, if you have information in terms of sigma and epsilon, then you can use this treatment over here, these formulas. And if you have the information in terms of real and imaginary part of the epsilon, then you can use this formulation over here. You can use either of them, whichever gets you the result faster. So we have already defined this standard as a ratio of the real and imaginary part of the permittivity, and we call this as the loss tangent of the material. And once we have got our electric field. So we started with the Maxwell's equation and then found out the electric field on the previous slide, and then now we can calculate the magnetic field by using the second Maxwell's equation, and uh, which will be given something like this. So, and this is all mathematics. If you try it by your hand, you'll be more able to follow it. So this might look complex, but it really not is. So this you only need since or in the previous slide we already had defined the electric field. We just took the derivative and multiplied it with these terms, and we got our magnetic field over here. And again, then we define the intrinsic impedance. But since this is now complex, the intrinsic impedance will become complex. Again, complex means nothing. It just means that if when the wave is traveling from one medium to the other, it will experience a change of the phase. So if there is a field E1 in one medium and there's a field E2 in the other medium, at the interface, you will experience a change in the phase uh, nothing more. And then we can simply write the magnetic field by uh, in terms of intrinsic impedance and the electric field and the propagation constant. Now coming to plane waves in a good conductor. So a good conductor uh, is a more realistic thing because uh, we in a lot of cases we just assume the conductors to be perfect electric conductor, that is it is perfect with infinite conductivity, but the conductivity might not be infinite in a lot of cases, and we need to study the behavior of the wave this in a more realistic conductor. So many of our practical issues involve loss or attenuation due to good but not perfect conductors. So that is the sigma is finite in this case, and the good to and a very good approximation for a good conductor is where you have sigma much greater than omega epsilon, but again not infinite. So most metals can be categorized as good conductors, and in terms of complex, if your permittivity, that is, if we are not talking in terms of sigma and epsilon, and we are talking in terms of real and imaginary part of the permittivity. So the we basically mean is that the imaginary part is much greater than the real part of the permittivity. So, using this approximation, we can get the propagation constant. So something like this, that we use in this particular approximation, and we end up with the expression for the propagation constant looking like this: j omega mu epsilon, root under mu epsilon, and then root under sigma by j omega, and one more term which was over here is now vanished. We can then simplify this to an expression looking like 1 plus j root under omega mu sigma by 2. So this is what your complex propagation constant will look like when you are assuming that the media is a good conductor. Now we can calculate the skin depth inside a good conductor. So in a PEC, the skin depth is 0, but in a good conductor, you will have some finite skin depth. I mean, which is defined as 1 by alpha, and so you have the propagation constant over here, which is alpha plus j beta, and now you can just by visual inspection, you can see that alpha is equals to 1 into omega root under mu omega sigma by 2. So using this particular value and substituting over here, we get the skin depth as root under 2 by omega mu sigma. Now, the skin depth is actually means that the magnitude or the amplitude of the fields outside the conductor when it moves inside the conductor will decay by the amount of the will decay, and the skin depth is calculated when this particular amplitude becomes 1 by epsilon times or 36.8% times of the original magnitude which is on the surface. Now let's do a quick example, just looking at what we have done. Okay, before that, maybe we can take questions if you have any from uh, the plane waves traveling in a lossy media and plane waves traveling in a good conductor. If you have any questions, you can either write it in chat or raise your hand. Uh, that will let me know that you have questions. So I guess The questions now. Yeah. Also, since all these things are already part of electromagnetic theory, which is also a prerequisite for this course. So these things might be simple all to you. Then we'll move to the numerical that we are about to solve. Okay, so Vinay's question is, can the explanation of lossy and lossless transmission line using schematic diagram? Okay, yeah. Vinay's will be starting with the transmission lines in the in a few more classes where we'll discuss the transmission lines in detail, starting with the telegraph equation. Right now, we are discussing plane wave propagation in dielectric media. So in transmission lines, we'll be dealing with voltage and current, and and then we'll have the RLGC terms. So I think that will explain the things better. Um, right now, if you have any questions regarding the propagation of plane waves in lossy and lossless medium, maybe I can deal with that now and take this question when we have discussed transmission lines. Yeah, okay. Yeah. Okay. So no follow-up questions then. I see that you've written so far things are fine. Okay. So maybe okay. So I'll wait for a few more moments if anybody else has any questions and they are unable to turn their mic on. Maybe we can uh, put up their questions in chat. Meanwhile, you can try solving this particular numerical where we have to uh, calculate the skin depth for these four metals: aluminum, copper, gold, and silver, at a frequency of 10 gigahertz. So I've listed the conductivity of these metals over here, and the frequency is already mentioned. So skin depth is, if you can recall, is root over 2 by yeah, so root over 2 by mu sigma epsilon, something like that. Yeah. So, okay. So maybe I can give this hint to you. So omega mu or sigma. Okay. And all you need to do is substitute the value of omega mu and sigma. Sigma is listed over here. Omega is given over here as 10 gigahertz. Make sure to convert this into radians. Yes. And then for each metal, you'll have to substitute the value of conductivity. So what we can do is we can just uh, put the values of frequency and permeability together and get this particular relationship where uh, the only term we need to change is sigma for each of the metals, and we can get the answers. I guess so. No questions from what we have discussed so far, and we are doing this numerical now. So maybe sort of just post keeping the answers on screen. I'll wait for some time if you anybody wants to do this exercise. Maybe it will help you keep motivated for this particular course. Yeah. So nothing tough in this. You just need to use your calculator and put in value and get the results. So this formula is over here as well. Okay. So I hope if you must have tried it yourself. So for aluminum, the conductivity is listed over here as 3.81. So we put in that value, and so definitely not mental maths for me, but yeah. So put in the values on the calculator, and you will get the skin depth as 8.14 into 10 power minus 7 meters. Similarly, we do it for copper and we get the value as 6.60 at 10 power minus 7 meters. For gold, we get this as 7.86 into 10 power minus 7 meters. And for silver, we get this as 6.4 into 10 power minus 7 meters. So what you can see is that the skin depth uh, uh, so you can see what you can see is that the skin depth actually becomes lesser as the as we, for the skin depth is lesser for but like what we consider as a better conductor. So we know that this silver is the most preferred conductor in using in wiring and things. So yeah, the skin depth is very less than and as compared to aluminum, which is also used for wiring. But again, this has it's a higher skin depth, but it is preferred because it is a cheaper metal. Then in between is copper, which is preferred for most applications. That it has a very less skin depth and is relatively cheaper. Is much cheaper than silver and yeah, relatively expensive than aluminium. Yeah, so I uh, this is a summary. I'll just put this slide in, put this table from boards are in other slides, just in case if you are referring to whatever has been taught and quickly use it as your a guide or a formula cheat sheet if you want to like if you are want to recap through things. So listed uh, the propagation constant, phase constant, attenuation, impedance, skin depth, wavelength, and phase velocity for lossless, general or lossy media, and in the case of a good conductor, where we are using this particular approximation. Yeah, you can use this as a reference while doing numericals as well. So we'll start. So now we'll start with general plane wave solutions. Maybe we can take a moment looking to look at this table now, and if you have any questions, we can take. Otherwise, in some moments, we'll start with the general solution of plane waves, and after that, we'll discuss circularly polarized waves, and then and that will be all that we'll be discussing today. So, some more topics to go for in today's class. Okay, so so now we'll start looking at these general solutions to plane waves. So in free space, the Helmholtz equation for electric field can be written as del square E plus k naught z square E equals 0. And we can expand this. Del. Yeah, sorry about that. So we can expand this del in terms of derivatives like this. So it equals to 0. And where k naught, where this k naught is the wave number. Now, yeah. So this particular wave equation holds for all the three electric field components, which is Ex, Ey, and Ez. So for all these cases, we can so instead of using Ex or Ey, Ez, we can use this general term to express. this Helmholtz equation for each rectangular coordinate of the electric field. Now, to solve this, we use a method called the method this separation of variables, which is a very common method in partial for treatment of partial differential equations. So this comes under the graduate level mathematics. So treatment is very simple. Where what we do is we solve for x, y, and z this derivative separately. So it begins by assuming that that each of these the solution for each of the field. For example, if you're solving this particular equation for electric field in the x direction, so this I terms will be replaced by ex, and we assume that the solution can be given by by in terms of the by functions in three separate functions multiplied together. So we are assuming that the electric field will be of some form like this. So f is a function which is only dependent on x, g is a function which is only dependent on y, and h is a function which is only dependent on z, and their product together is what will give a solution to the electric field in the x direction. And similarly, we'll assume the solution for Ey and Ez as some functions, product of some functions. So, and in which the individual functions are only function of either x, y, or z. Yeah. So, we started with the Helmholtz equations, and then we expressed then we expressed the Helmholtz equation for each rectangular coordinate of the electric field. And we'll focus right now on solution for only the ex, that is over here we're putting I equals x, and now we are assuming that the solution will be of something of this form. Now when we again, since we our assumption of the solution, we what we do is we again substitute it back into this differential equation and divide it by f, g, and h in the functions. And this will end up in something we'll end up with an equation looking like this, where f double dash and g double dash and h double dash, these are the second order derivatives. Yeah, sorry about that. So we will end up with an equation which looks something like this. And now, the key step to the solving this equation is that we uh, we uh, we know that the individual terms are equal to constants, because we know that f is only function of x, g is only function of y, and h is only function of z, and k over here is a constant. So from this, we uh, we know that each of this term will be equal to some constant. So what we'll do is we'll assign this each individual this fraction equal to some constant, and then solve them independently. Yeah. So we started with the Helmholtz equation. Then we decided that we'll solve for individual rectangular components for the electric field. We chose the electric field in the x direction. We assumed the solution to be of the form f, g, and h. And then we got this particular relationship by substituting f, g, h inside this equation back, and dividing by the LCM. Now we so now since we to solve this particular equation, what we'll do is we'll take the individual fractions and assign it to some constants, and these constants we are choosing them as kx, ky, and kz. So yeah, so this is what we are going to do. The f double dash by f, it will be equal to minus of kx square, and g double dash g will be equal to minus of ky square, and h double dash h will be equal to minus kz square. or we could write them something like this. So d's second derivative of f in terms of x plus kx square times f equals 0, and similarly for g and h. So now this particular equation the solution is known to us, and it is of the form that we have already seen. Now, if we put this particular these terms back and we compare with this particular term, we get that a kx square plus ky square plus kz square will be equal to k naught square. So the only thing remaining from over here was the k naught term, and so once we have solved the equations over here, then from the known values of kx, ky, and kz, we can find out the unknowns from here as well. Yeah, so starting with the partial differential equations, we divided them into three different ordinary differential equations, and solution to them are of the form e power jkx, e power jkyy, and e power jkzz. So for each of these terms in this, we know the solutions, and yeah. So using this particular form, we have the solution for the electric field in the x direction as a e power minus j kx ky and kz. Yeah. So and a over here is some arbitrary constant that we are using to write the solution. And to get this value of a, what we do is, if we know the source and the boundary conditions, we will be able to evaluate the a as well. So now we define a wave number vector k as this particular expression over here in the exponential. We can define it as a wave number vector, and we can again if we can denote it using k naught as k naught n cap, where n cap is the direction of the uh, uh, propagation of the wave. Yeah. So and the magnitude of the this particular vector k is given by k naught. And again, we define this particular vector r uh, as the point in the space, and using this r over here and k over here and this expression, we can write the final solution for E field in terms of a e power minus jk kr. So yeah, so doing all these steps, we can just define, we get the solution for the electric field individually. And now we'll use, and so using the same things, we can get the expression for EY and EZ as well. So I'll maybe stop over here, take some, like we'll pause over here and take some questions if you might have any like from this particular derivation. I hope that this thing was clear to you, pretty straightforward. We're just doing mathematics, not much complexity involved right now. But if you are stuck at any particular step, we can maybe discuss. Okay, so I believe no questions. If you have any, you please feel free to post your question in the chat. We can take them now or later. Yeah, so we'll proceed. So till now, what we have seen that we started with the Helmholtz equation, and we wrote them individually for each of the rectangular component of the electric field, divided them into the three different separate differential equations, and we have solved them for the x component of the electric field. So we have the results for the electric field. Now, using the same treatment, we can write the solution for EY and EZ in terms of like this: V e power j k r and C e power minus jkr, and where b again b and c like a are arbitrary constants, and their values can be calculated from the if we know the source and the boundary conditions. Now, going back to the Maxwell's divergence equation, we since we're looking at plane wave solutions, so we do not have any source. So the divergence of electric field will be equal to zero, and and this implies that and this particular equation also implies that the variation of ex, ey, ez they must be similar, because this we have the divergence of E field equals zero. So we started with the Helmholtz equation. We divided them into three components, and got the solution for the electric field, uh, x component, y component, z component, using the mathematics that we have done earlier. And we saw that we have the Maxwell's divergence condition, which states that the divergence of electric field, which is equal to zero. Now, if we, now the electric field can be if, can be written as a the different components of the magnitude of the electric field uh, in the different directions. This as the sum. So a x, by, and cz, and this is how we are defining. This is our electric field finally. Now we also have the final electric field is written. Uh, just a second. Yeah, sorry about that. So, so the final solution for the electric field can be given by this form. So the initial expression that we had started with was the Helmholtz equation, which is given over here as the del square E plus k naught square E equals zero. So its final solution will be of something of this form, where E is equals to E naught e power minus j k r, and E naught is again given by ax plus by plus cz, and the exponential terms we have already defined in the previous slide, where k is the wave number vector, and r, which is in the direction of the propagation of the wave, and r is the point at which we are referring to in the in the spatial in the space. Yeah. So so once we have already got this particular solution over here, so we what we do is we use the Maxwell's divergence equation, and we substitute the value of this particular value that we calculated, the solution over here, and calculate the curl. And now the solution, the operation of this particular thing, say we are using some identity. You can find that in the appendices of Boza. So what will end up is something looking like this. So jk dot product with electric field e power minus jkr will be equal to zero. Now this implies that the dot product of k and electric field is equals to zero. So this means that the electric field amplitude must be perpendicular to the direction of propagation. which is given by the vector k. So this essentially means that we do not have any electric field component in the direction of the propagation for in a plane wave. Now we have used all this treatment to calculate the value of electric field. Now to get the value of magnetic field, all we need to do is perform this curl operation and then divide it by j omega and mu naught. We will get the value of the magnetic field. So doing that, we substitute the value of the electric field, perform the curl operation. And what we end up is all we need all we end up with this particular expression where the where n is the normal vector, the propagation of the direction of the wave, and E is the electric field. So we get this generalized expression. So if we know the electric field, we can calculate the magnetic field by just doing a cross product uh, with the normal vector in which the direction of the which is in the direction of propagation. Now, yeah, and this result also shows that the magnetic field vector H lies in a plane which is normal to K and in the direction of propagation, and uh, normal to K, which is in the direction of the propagation, and H itself is also perpendicular to E. So if we for any general vector which is given by A equals B cross C, so we know that A is perpendicular to both B and C. So similarly, the H is being expressed in terms of N and E, and N is in the direction of the propagation, and E is in the direction of the electric field. So H is both perpendicular to the direction of propagation and electric field. So again, this also means that there is no uh, magnetic field component in the direction of the propagation. So we can express the we can so this diagram shows the for a wave propagating in this n direction. So n is also uh, the direction of k. You can see where k is being expressed in terms of the the unit vector n cap over here. So we have the electric field and magnetic field both are perpendicular to each other and in the direction of propagation. So for a plane wave, this is the criteria that there we do not have any electric field or magnetic field component in the direction of the propagation, and E field and H field themselves are perpendicular to each other. So this is all the condition and derivation for a general plane wave. So we started with the Helmholtz equation and showed that we for a plane wave we did not have any component in the direction of propagation. Yeah. So we'll maybe pause over here. Take any questions you might have from the solution of a general plane wave. Okay. So I believe no questions. So this I believe this is a very standard formula for you now. The H is equals to 1 by n naught, where n naught is the intrinsic impedance of T space. N cap is the vector in the unit vector in the direction of propagation, and E is the electric field. So yeah, this you must be using this quite often and after the in your electromagnetic theory courses. Coming to circularly polarized waves, so what we have discussed till now was where we had the electric field only in the x direction, and we call them as linearly polarized waves. But quite often we come across the term known as a circularly polarized waves, and even in antenna design and among antenna engineers, circularly polarized antennas and is very popular. So, what do we know? What do we mean when we say we are working with the circularly polarized waves? So, all this discussion we did now was that we had an electric field which was in a fixed direction. Uh, so the electric field vector was always pointing towards the x direction. And similarly, we had with the wave was propagated, if the wave was propagated in z direction, our magnetic field vector was always pointing towards y direction. But what happens if this particular electric field vector is the direction of this electric field vector keeps changing? Uh, so the polarization of a plane wave refers to the orientation of the electric field vector, which may be in a fixed direction or may change with time. So the electric field, maybe I can use uh, pen right now. So if the electric field vector always points in one particular direction, so this is our coordinate system. So this is x and this is y, and if this is x, y, and then so the z will be inwards. Yeah, I think that's correct, right? Yeah. So if the electric field is always pointing towards the x direction or it is always pointing towards the y direction, uh, they are it could be in this way, or we might have in some cases where the electric field vector is sometimes pointing in the x direction, and then it might sometimes point towards somewhere in between the x and y direction, and sometimes points towards the y direction, and might even end up changing all the way through and going in somewhat this fashion. So this is if it keeps rotating like this, and the electric if this particular electric field vector forms a circle, we call them a circularly polarized. So we'll look into this. So what we're saying, what we're trying to say is that this particular the direction of the electric field vector might not always be in this one direction. It might also change. So if you right now, for example, if you take a superposition of this electric field vector in the x direction and electric field vector in the y direction, we can total field we can write in something like this. So E1 is in the x direction and E2 is in the y direction, and the wave is propagating in the z direction. So the total electric field is can be written in this fashion. So we have now can have some of these cases where the electric field in the x direction is non-zero and electric field in the y is zero. So the will have a plane wave which is only polarized in the x direction. Similarly, if the E1 is zero, where that is the electric field in the x direction is zero, and electric field in the y direction E2 is non-zero, we have a electric field polarized in the y direction. But what happens if both of them is not zero? So both if both of them are non-zero, we might have we will end up with a linearly polarized wave. So this will probably point in some in this direction. So this will be direction of the polarization, which is neither in x nor in y, but somewhere in between x and y. And the angle which the this electric field makes can be defined as something by phi, which is the tan inverse of E2 by E1. So this is the angle of the polarized angle that we can define it as E2 by E1. So E2 is essentially in the y direction and E1 is in the x direction. Now, consider if we consider a case where E1 is equal to E2 equal to J times E2. So this uh, and which is equal to E naught. So essentially, we are saying that this is real, this is complex, and so the final total electric field can be defined as E naught x minus J y. So what will happen in this case, that we'll have a phase difference between the x component and the y component. And if you try to write this in time domain, we can write it's by changing from the polar to Euler. We can write it like this. Uh, so cos omega t minus k naught z, and we have this pi, and then minus pi by 2 term for the phase offset for to account for this minus j. And we if we try to so so what we see over here is and that the electric field vector is now changing with this time and space. Similarly, time and space. So the electric field vector is now changing with both space and time. And if we try to plot this particular vector, we'll see some shapes. Now uh, see, we what we do is we can take a particular. Um, so if we choose let's say z equals 0, we can express the electric field in something of this form. So this particular minus pi by 2 is account changes this cos to sine omega t. Now, and to calculate the resulting angle from so which it forms. So the polarization angle can be calculated by using tan inverse of sine omega t by cos omega t, which effectively form uh, 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 ends up with we end up with omega t. Now, what we see is that if we this particular polarization angle is changing with time, and if we try to plot it, so okay, okay, back to pen. So if we have the x-axis over here, y-axis over here, and this particular angle which it makes with the x. Uh, for example, if this is the direction of the electric field, and this was the phi that we are calculating, we are seeing that this particular phi is changing with omega t. And as the time increases, this particular phi increases and then uh, comes back to this original position, and this particular angle is changing. And now, since we have already assumed that the the electric field components magnitude in x and y direction are same. So what we will see is that this particular pointer will always form a circle. So this particular thing, if the so we are seeing that the electric field vector is actually tracing a circle, and hence we call them as circularly polarized waves. So we started with we took a case where the electric field we had the E1 in the x direction and E2 in the y direction, and they were related like this. And we wrote the equation for the electric field, expression for the electric field, and we expressed them in the time domain form. And at particular instant z equal to at particular point z equal to 0, and we calculated the polarization angle, which came out to be omega t, and showed us that the polarization changes at a uniform angular velocity omega. And so we'll see this in the just next slide, that we call this particular case this particular wave as the right hand circularly polarized wave. And similarly, if it was plus j over here instead of minus j over here, will we have a wave which is we call as left hand circularly polarized wave. Let's take a look at these two figures. So you can see that we have x over here, y over here, and z over here. So if we see that the so for this case, we found out that it was omega t. Now, as time changes, it will trace the polarization angle. This phi will rotate like this, in this fashion, and the direction and the propagation of the wave will be in the z direction. So if you point your thumb in the direction of propagation, you'll see that the angle the rotation the direction of the rotation is uh, uh, anti-clockwise, and you can show this particular the action using your right hand. So if you point your right hand thumb in the direction of propagation, the other four fingers will point the direction of will trace the electric field vector. So this is why we call it as right hand propagation. And similarly, for the second case, you can see the polarization angle, the phi is in the clockwise direction, and if the wave is propagating in the z direction, this particular this part- if you point your left hand thumb in the direction of propagation, you'll see that your the other four fingers are tracing the electric field vector. So that is why for the second case we call them as left hand circularly polarized rays, because they're tracing a circle, and by using your left hand you can demonstrate the direction. You can find out the direction of propagation if you know the rotation of the electric field vector. Yeah. So that was all we plan to cover today. We'll stop over here. Take any questions that you might have from the previous classes, or what we covered from today, and yeah. So then we'll conclude over here. The next class. So today we covered the wave equation and general plane waves solutions. In the next class, we'll look at energy and power, and plane wave reflection from media interface. Okay. So any questions you have from today's class or from previous classes? Otherwise, we'll end up end today's class over here. Okay. I You can take your time. You can I'll share the slides and the recording in some time in the WhatsApp group. Um, and Yeah, you can post your questions on WhatsApp, or reach out to me on email, or we can take your class questions in the next class. So then I'll stop the recording over here.